Thomas, if he was that a volunteer, or was that just a test? Great, thanks a lot, Watson. Right, I think we can begin. Let me share the screen. Right, good morning all. We are here on the final day of IETF 110. I'm Shivan, and I'm here with my co-chairs, Chris and Sarah. And somewhat early for me here on the Canadian West Coast, but I'm hoping this will be a fun meeting for everyone. Friendly reminder that the meeting is recorded. You might have already seen this slide at this point in the week, but just a friendly reminder that please do read this note well before participating today. And oh yeah, and also a reminder that if anyone wants to participate in the queue, please press the raise hand icon, and yeah, and then you can send audio separately. And also please remember that Pearg is a part of IETF, which is a research organization and not a standard setting organization. So I will be going over the status of the various drafts that we have. So 2 of our numeric identifiers drafts are right now in the IETF chair queue. They should be going to RSG last call. They passed the research group last call last year. And the rest of our drafts, a couple of them, I know the authors are working on updates, and draft censorship is actually not on here. Stan Adams from CDT will be giving a quick update towards the end of this meeting. And we did have an interim on IP address privacy in January that Chris will be giving an overview of. But we do have Brad Lassie and Paul Jensen talking about NatCatcher, which was a talk that was presented at IP address privacy interim, but we didn't have enough time for that. So this is the full talk. And we'll have some discussion time to talk about that interim and what themes emerge and what the potential work is around that. And we will also have a talk by Zach Newman, who will be talking about their work on using overlay routing for improving performance for anonymous communication systems, specifically Tor, which should be interesting. And then, yeah, like I mentioned, Stan Adams will be giving an update on the censorship techniques draft. All right, and we can also try out this countdown timer thing. So, is there anything else that I'm missing? Nope, yeah, so if Paul, you wouldn't mind sharing your slides, we can get started.
I think I requested.
Oh, well, I don't see your request. Would you mind doing it again? I just stopped my screen share. Oh, there you go. Oh, perfect.
Cool. So my name is Paul Jensen. I work on Chrome on the Privacy Sandbox team, and I'm here to talk to you today about the gnatcatcher proposal. So gnatcatcher is a bird. Here's a picture of a gnatcatcher, but it's also the name of this proposal. It stands for Global Network Address Translation combined with audited and trusted CDN or HTTP proxy, eliminating re-identification. So in terms of where this proposal comes from the Privacy Sandbox team, which is a team that aims to eliminate cross-site identity linking. We're working towards a big first step of deprecating third-party cookies. And as we work towards that, we need to make sure that we're not allowing other mechanisms for identity linking, and IP address is a pretty big one. So how can we improve IP address privacy to prevent this linking? So we can give each person many addresses, one per tab, one for each site you go to kind of thing. We can give many people one address, so sites can't tell which person's behind it. And we can also make servers not use IP addresses for identity. So let's look through those solutions. So the first solution, give each person many addresses. These days, with the number of internet users, it's only possible with IPv6. Right now, a lot of people are using Slack for IPv6 to get their address. And the problem is that a lot of the time they still have a big prefix that's unique to them. And so even if they have multiple addresses, they'll all have the same prefix, and it's not really providing any privacy. We could start giving people lots of random addresses with different prefixes, but the hierarchical nature of the internet kind of breaks down, and it becomes very challenging to route packets at scale. The router caches kind of explode. So moving on to the two remaining solutions, we paired them up into a hybrid of the two. So in the give many people one address front, we have a proposal called near path NAT. And in the make servers not use IP addresses for identity, we have the willful IP blindness spec. And so NAT catcher is the hybrid of these two, it puts them both together. So I'll walk through willful IP blindness first. So willful IP blindness, the idea is that servers on the internet attest to not using IP addresses to track users. And then they volunteer to be audited to verify that they're telling the truth and to verify the degree to which they use IP addresses as identifiers. And once they complete this audit, they're then given a certificate that they can in turn take and show to a browser. And then the browser can use that to adjust things like the privacy budget to control how much access to other identifying information they have. So the basic idea is the server has already decided not to use IP addresses for tracking, and then they attest to this, and then they're audited to verify that, and then they're given the certificate. Obviously, this is not an easy thing. The audit has a lot of complexity to it. So I'll walk through a few of the different areas that are still needs for using IP addresses. And so these are areas where the audit has to verify that they're not using it for identity. So the first and most obvious case is using IP addresses for routing packets. The hope with willful IP blindness is that we can divide the server stack into two sort of halves. The first half has access to the IP address, but doesn't have access to application data. And the second half, the sort of deeper part of the stack, the application backend, that part does not need the IP address necessarily, but it does need stuff like URL, user ID, cookies, things like that. And so the idea is that by dividing the serving stack into these two kind of pieces, we can make it easier to audit one and the other, because if we know the IP address isn't getting to the back end, then we don't really need to audit that because they can't use it for joining if they don't have it. And the other advantage of dividing it into these two sort of halves is if this first half is stuff that's generally done by a CDN, this could become something a CDN could offer to the application backends they're hosting. So they could say, okay, I've been audited. I know I'm conforming to willful IP blindness, and I'm not using IP addresses for re-identification purposes. So we now know that the services they're hosting are also conforming. IP addresses are also used for server selection. So a lot of the times you'll have multiple servers and they'll be hosting different content. And so a site might need to pick the server that's closest to the user for the best latency and the one that has the content that they're looking for. This can be a little tricky because you're taking into account proximity, which could be based on IP address, and you're taking into account content, which also could share some identity. And so this is an area where it has to be audited to make sure that it's just being used for this server selection. It's not being passed along for re-identification. So in the interim IETF Pearg meeting we had talking about IP address privacy, there are a number of presentations about anti-abuse applications of IP, and so it's clear there's a lot of uses there that are really important to the success of the web. And so we need to make sure that the willful IP blindness policy can account for that and keep those important functions working. So a lot of those anti-abuse things like denial of service, botnet detection, like some of that can be done at the CDN level. And so as I was saying, like if we can divide serving stacks into two sort of parts, the sort of CDN-ish part and the kind of application backend part, and then we can allow the CDN part to use the IP address for things like anti-abuse. But we know that they're not joining it because the sort of user identity is kept more in the backend, in the application backend. So there are cases when IP addresses are used for anti-abuse purposes a little deeper into application backends. But the idea is you could kind of hopefully compartmentalize and separate those from the rest of the application backend so that we can still audit that and say, okay, the IP address is not leaking back in, but it is used in these little parts, but those parts are only outputting like abuse signals. And at the same time as this all can be audited, the hope is that there's other privacy preserving alternatives that are going to be coming online that can decrease this reliance on the IP address. And so it can make the audits easier if, say, someone's using like a trust token to convey the trust rather than sort of associating the trust with an IP address. And so over time, the audit can become easier as these technologies evolve. IP addresses are also used for rough geographical inference. A site might need to know roughly where a user is to apply region-specific treatments. So think like GDPR or CCPA. And so willful IP blindness needs to allow for that and needs to audit to make sure that only coarse geographic location is used and is only used for applying these region-specific treatments that are necessary. There are also rare cases when you might need to use an IP address. So for example, if somebody comes to you and says, you know, I'm getting really bad performance, here's my IP address, and you sort of have their permission to look in the logs for it. So you might need to debug like one particular address here. Also, if there's some really dangerous abuse going on, you might need to investigate further. So in these cases, you need to audit to make sure that when this is done, when IP addresses are used for these specific rare events, that there's sort of a break glass access is required. And when that happens, we need to make sure it's logged. We need to make sure that log is auditable and people are providing motivation. And the most important thing is we need to make sure that these are in fact rare events and that they're a small fraction of all the traffic and all the IP addresses that are coming to a site. We want to make sure this is only being used for sort of rare investigations. So as we were kind of thinking about willful IP blindness, you know, we're keeping in the back of our minds that this is sort of feeding back into the privacy budget, like I was saying. And so looking at the sort of this identification based on IP address, if there's 7 billion people, and this means we need roughly on the order of 33 bits to uniquely identify everyone. And a quick look says that IP addresses are somewhere in the neighborhood of 27 bits of entropy. There's a little bit of instability there, depends on your audience, et cetera. But the fact is that 27 bits of entropy is almost all of this 33 bits of entropy. So it's a really big problem. And you know, willful IP blindness makes sense in some cases, but for sites that aren't willfully IP blind, they're still going to have almost no privacy budget. So we really need another piece to this puzzle to solve it. And so this is where NatCatcher comes in. So NatCatcher, as I said, is the hybrid of willful IP blindness and the near path NAT. And so by bringing in the near path NAT proposal, NatCatcher becomes more of a complete solution. And by having willful IP blindness, we still allow for sites that need to do perhaps cross-site anti-abuse measures so that they can keep working. So the near path NAT. So the near path NAT, the idea is that you basically run a NAT at the edge of the internet, perhaps at the CDN level. And we sort of call each of these NAT machines, or each machine running the NAT, an IP privatizing server, so an IPPS. And so these IPPSs, their function is to make sure, so they're basically natting the traffic coming from clients, and they're sharing their IP address amongst thousands of browsers. So sites can't really tell which of the browsers it is. And they can also kind of change the IP address and port as you go between different sites. If you have IPv6, they could just change the IP address so that as you're browsing across sites, they can't re-identify you based on your IP address because it's changing. So the kind of rough diagram of how near-path NAT works, your browser establishes an HTTP3 session to the NAT, and inside the session, you've got streams for your TCP and your UDP connections. And then when those come out the other side of the NAT, like a typical NAT, they're given the address of the NAT rather than your address. And you can see in this example, when you're talking to two different servers, the address that you present to them is different. And then, of course, you're not the only person talking to NAT. There's thousands of others. So, these same addresses can't be associated with just you because other people are using them as well. So the important thing for the near-path NAT is performance. And so it's not slowing down people's browsing experience. And by being near path, on the edge, they're not really adding to your length of your route between, your browser and your server. We're basically not sending data all the way off to a data center somewhere and then all the way back to wherever your server is. So the hope is that we can keep the latency down by being very close to on path. So as we talked about with willful IP blindness, there are cases when rough geographic location is important for region-specific treatments. And so with the near-path NAT, because we're at the edge, we're pretty near to those clients. And so the idea is that the IP addresses from those IPPSs can still give rough geographic information to apply the region-specific treatments. So we can still support that use case. So as I said, as you're going to different sites, the IPPS is presenting different IP addresses to different top-level origins. So if we take this mapping from one person going to one top-level origin, and then we're mapping that to the IP address or port tuple that we're sending to that server. If we keep that mapping constant over time, then it allows servers to do some of the same anti-abuse mechanisms that they have been doing in the past. So if we have IPv6 between the IPPS and the server, that allows us to present a unique IP address to each server. And so if the server has some sort of legacy anti-abuse where they're just looking at the IP address and blocking ones that look like abuse, they can continue to do that because the mapping is constant for the client to the top level origin. So in this way, we can sort of keep the anti-abuse mechanisms working, even though we're natting the traffic. So when we thought about how we can implement the near-path NAT, we looked around at a few different ways of technologies of doing that. The explainer sort of compares and contrasts a few of them. The thing that really seemed like pretty much a perfect match to the needs of it was the mask protocol that the IETF mask working group's working on. It's basically extending HTTP3 with proxying capabilities. And like that diagram showed before, like you have an HTTP3 connection to the IPPS, and then in there's TCP and UDP streams. And so it's a pretty good match. It also leverages a lot of HTTP3's strengths, very modern protocol, so the performance is good. It's got pretty good encryption. And a big thing too is that browsers know how to speak HTTP3, and a lot of servers do as well. So it's already deployed to some degree. So I think that's the end of my presentation.
Thanks, Paul. We don't really have too much time for questions, but Mark, do you want to go ahead? Okay. We also have 10 minutes for open discussion later on.
Yeah, I had a question of clarification. You said in a couple of the slides at the edge, and I may have missed it, but that means many different things to many different people. Could you talk about where you envision this being implemented and you know what you mean by the edge, and especially who runs that service?
So this is kind of a proposal, so I'm not sure we have any specific answers to that. You know, at the CDN level is one kind of answer. And in terms of who runs it, I don't know if there's a great answer. It doesn't have to be one person necessarily. It could be a sort of a service that multiple people are offering.
In general, it's the
Right.
realization that there are plenty of folks who have, you know, edge caches or CDNs or whatnot that are close to users, and those folks would be well positioned to run something like this in general.
Cool. I guess from a CDN perspective, that would be, you know, it looks pretty straightforward to implement, and it looks interesting as a service to provide customers, but it seems like you'd need a mechanism to communicate and to make the assertion from where you're performing the service back to the browser so the browser can change its behavior, and that creates an incentive for people to adopt it, and then you get a virtuous cycle. So that's, I guess, the piece that I don't see here yet, but it'd be really interesting to talk about.
Thanks, Paul. Thanks, Brad. Chris, do you want to give your summary of the interim?
Yeah, could you pull up the slides, please?
Sure.
All right, next slide. Right, so the interim that we had, I forget when it was actually. The entire focus is on IP privacy, trying to look at it from the perspective of clients and servers. We made sure we had discussion in terms of like how IP addresses are currently used for on the server side for various anti-fraud and abuse cases, and for denial of service prevention and mitigation mechanisms. And there's a lot of lively conversation that came out of that. There also were two great presentations on sort of the overview of the privacy aspects of IP addresses, both from the perspective of the client as well as from the server, and then various sort of forward-looking proposals about how to potentially deal with this, the problem of IP address privacy, from folks at Tor and other people at Google, and Brad had a very quick summary of Gnatcatcher and willful IP blindness, but thankfully was able to do the full thing just now. Next slide, please. So during the course of the presentation, a number of key questions came about. Perhaps the most important one, or in my view, perhaps the most important one, was that if you imagine a world in which IP addresses were removed from servers, be it by a Gnatcatcher or something else, what are the requirements for a signal that could be suitable as a replacement that would work for these anti-abuse cases, anti-fraud cases, and denial of service protection cases? And there was some discussion during the meeting, and then some follow-up chatter on the mailing list, or there was a mention on the mailing list that Matthew Finkel kicked off. And it seems like there's still some more work to be done in figuring out what exactly are the requirements here, both from sort of the client perspective in terms of what are the privacy properties that they want of the signal, as well as from the server's perspective in terms of what are the, the authenticity properties of this particular signal. Can it be spoofed easily? What's the granularity of the signal, and so on. Something also interesting that came up was the need for analyzing the cost benefit of using IP addresses in the way that they're used right now. So clearly, folks have concerns in terms of how people use or misuse IP addresses for from a privacy perspective, and but using them in this particular way may make it cheaper, easier, et cetera, to do certain things on the server side. So looking at exactly how the costs shift for various parties involved as you either take away IP addresses or replace them with something, certainly would be quite useful. Another interesting point that came up was sort of the differences between v4 and v6 addresses and how they affect the signal entropy. Fernando had some good comments on that. And then thinking specifically about this signal, the question was raised whether or not sort of an unspoofable signal of remote attestation that the device is trusted, like that the client device is trusted from which the connection is coming, would be sufficient. There were also mentions and references to sort of anonymous credentials as a more general mechanism here. And folks perhaps are aware that there's work ongoing in the privacy path space, which is a particular type of anonymous credential. Maybe there are applications there. I think what would be quite useful is to, I think, have more discussion around the first point here. We really need to sort of get clarity in terms of what the requirements are from all parties involved, and that would allow us to kind of embark upon finding a suitable replacement. So that's effectively the high-level summary. And how much time do we have for sort of discussion, Siobhan?
9 minutes.
Okay. So as next steps, I think it would be good to, like I said, document these requirements. Pull people into the conversation that represent both the clients and the servers, because sometimes these requirements are at odds. But I'm sure we can come to consensus here. And once we have sort of an understanding in terms of what is actually necessary for this particular signal, then maybe look at how existing technologies that are being standardized either help or don't help, and like what is the gap between what we have available to us and what needs to be done in order to build it. In doing so, it might be worth also considering sort of the larger impact on this sort of shift on just the ecosystem in general. Like if you're going to do something similar to Gnatcatcher, how do clients actually pick proxies? How are they audited? How are they trusted? What are other aspects of centralization that we'd be concerned about? And perhaps also logistically speaking, we should decide where this work should take place, be it in Pearg or elsewhere. I have no strong opinions there. I think it's useful work, so it could probably happen anywhere. So with that, I'd like to just open the floor to discussion. So if you have thoughts in terms of signals, requirements, happy to hear it. So, and I'm going to mute now because there's background noise.
So everyone, yeah, please join the queue. Go ahead, Brad.
Yeah, I just wanted to jump in and say, we have a pretty strong interest in pursuing various some form of IP privacy. One of the big challenges is doing that and still preserving anti-abuse and anti-fraud protections so that websites can reasonably defend themselves against attack. So having a forum where we can discuss the needs there and how various applications could affect those needs would be great. So I'm very supportive of this.
Cool. Stephen?
Yeah, just as to kind of venue and kind of scope, I think Pearg is probably a good venue because it would allow, or more easily allow, including within scope, for example, the fact that some particular brands of mobile operating system might be returning an IMSI to an operator or a service provider as well as an IP address. There's probably a bit of a danger that if we move this work to an IETF working group, it would focus solely on IP address only mechanisms, and that might not solve the actual problem that we have.
What do you mean by IP address only mechanisms? Just that it would hyper focus on that as the specific vector, or
Yeah, so I think PRG allows people to kind of think more about the fact that like IMEIs and IMSIs are also identifiers that are as identifying or more identifying than IP addresses. I think that it would be easier to keep that kind of scope within the discussion in PRG compared to very much focusing right now on mechanisms for hiding or affecting IP addresses.
gotcha. Yeah, I think that makes sense. Certainly, we don't want to overly constrain ourselves so that we don't actually solve the problem of privacy from a client's perspective. So yeah, I totally agree with that. Matthew?
Yeah, I just want to say that I think any work in this area probably won't result in a single drop-in replacement for IP addresses, and we might need to look at different solutions for different signals, and basically providing client-side information to servers if it's not directly available.
Yeah, that's compelling. I mean, there's a lot of different signals that we extract from IP addresses, or that I gather from the interim. Geolocation, identity, and it might be the case that addressing each of these use cases requires like a different mechanism.
Yep.
So yeah,
That's my thought.
Andrew?
Yeah, just wanted to drop in the thought that I think it'd be useful to include network operators in the discussion, be they sort of enterprise networks or indeed sort of public networks, just to make sure that stuff isn't broken inadvertently, or makes it hard for the operators to discharge their responsibilities about efficient network management, including sort of spotting things like network abuse applications and so on. Just wanted to make the point. Hopefully, that isn't overlooked as one of the downsides in making things more private.
In some cases, these two are always at odds, and that's specifically why we want to have the people who are using IP addresses in the ways that they're using them right now in the conversation, so that we can as a group come together and figure out what's a good or suitable set of replacements if needed. There's going to be a conflict. That's unavoidable, I guess.
Yeah, absolutely. I just think it's important that it's understood in advance rather than only afterwards.
Noted. Stephen?
Yeah, sorry, I forgot to ask you something. So one issue with IP addresses is how they're used in trace headers in mail. And again, there are similar anti-abuse mechanisms that make use of those. Is that an area, I mean, is that something that should be in scope, or are there people interested in this, or are we really just thinking about the web?
That is a good question. I don't know. I'd be curious to hear what other people think. Certainly, the web is a motivating use case in this particular context, but it may be wrong to, I guess, constrain ourselves to that particular case to start. So, if others have opinions in terms of like what the scope should be, love to hear it. Yeah,
so I think some of the anti-abuse mechanisms may be a little bit different in mail, but I'd have to think about it more and talk to other people really. So, for example, I think in mail, some people may treat messages more likely to be spam if, depending on the set of IP addresses in trace headers. And that's a little bit different from the web anti-abuse patterns, maybe. So there might be something to learn by broadening the scope to include mail as well.
That's a good point. Do you know if the people in that space are in Pearg, or they're aware of this work? And if not, like, would you be able to like sort of help us bridge the gap?
Yeah, so there's an organization called MOG, which is kind of deals with that, with mail kind of stuff, and there's overlap between IETF and MOG, which is sufficient, I think. But I can certainly help if need be. The one thing I would say is that I think the mail anti-abuse people are even more allergic to changing things in terms of IP address handling than the web anti-abuse people. So it might be a challenge.
That's surprising. But yeah, good to know.
Chris, I was just going to mention one thing, a proposal that I think I remember from the interim, which is that I think it was Christian Hoytmer said what we could start with is an analysis of all the use cases with some assessment and categorization in terms of who's the primary protectee of the action, the anti-abuse action that's being made, and then categorize them. And then in that way, what might fall out is groupings for different signals with different nature. So I'm wondering if that's a piece of work we should think about trying to get started before we jump into the solution space too much.
That's what I mean by the requirements. I'm sort of assuming that work folds into this. We need to understand all these cases in order to understand like the requirements for what the solutions would be. Definitely think it's premature at this point to try to start speculating what would be a suitable replacement without fully understanding the problem. Yeah.
Are there folks interested in writing up a requirements draft? Is there, and we can ask this question on the mailing list as well, but it seems like that's kind of where we're converging.
Yep, looks like it. So I guess what we can do is send out a mail to the list, asking for people who are interested in working on this thing, and we can spin up a doc on GitHub and start working on it there. Unless someone else has a more concrete proposal, I think that's a perfectly fine way to start.
Yeah, I think so too.
Cool. All right.
Right. Joey, did you have a last comment?
Yeah, wondering if just to see if I can get your opinion. Yesterday, Medina's was meeting, and they are very interested in the use cases that are broken with the MAC address randomization. So I was just wondering what you guys think might be like the type of response for this IP use cases that you guys have in mind right now. Did that make sense, Shuan?
Yeah, which working group was this, Joey?
The Medina's buff, they met at the last IETF saying that it was a non-work group conforming buff, but right now they're already working on drafts and everything. Basically to circumvent, they are first gathering different use cases that need MAC address randomization circumvention,
right?
And they're also like gathering different solutions that are available for that currently.
Brad, do you want to talk to that?
I think this goes to Stephen's first point of whether the scope of this is just IP address or it covers MAC addresses and IMEI numbers and whatnot, other network identifiers that are associated with the hardware.
Yeah, I think that's in scope generally. I think when we are thrashing out what the scope is formally for the requirements document, we can just kind of make sure that we include this as well. Thanks for that, Joey, and thanks for the link. All right, I think that's a good ending point. We can move on to the next presentation, which is by Zach Newman. Zach, are you around?
I am.
Awesome. Let me grab screen.
All right.
And hello, Kyle, as well.
All right. So yeah, thanks for having me, everyone. My name is Zach Newman. I am here to talk today about routing for anonymous communication. And this is early stage research work. It's joint with a couple of colleagues, Kyle Hogan, who's here today, Sasha Serban-Schreiber, we're all at MIT, and then Ben Weintraub and Christina Nita Rotaru at Northeastern. And Ben is also in the audience today, and Kyle's here too. So the primary question we're trying to address is, can overlay routing benefit decentralized systems? And we'll go into more detail about what all of that means. But the main question is, there's a technique used on the internet called overlay routing, primarily by CDNs. And we would like to get some of those benefits of that technique outside of the CDN context. And so we're doing a case study on anonymous communication. And when one wants to do a case study on real deployed anonymous communication, you basically have one choice. It's Tor. Anonymous in the sense of metadata hiding, not end-to-end encryption a la Signal. And so when we're doing this case study, we need to consider application goals. It doesn't do anyone any good to make Tor a little bit faster if it's at the expense of privacy, for instance. And so today we're going to explain the high-level idea of this proposal and present a little bit of preliminary evidence in favor. And in the future, we'll hopefully have more evidence. We'll build out a proof of concept, do more analysis, do some simulations. And so I'll detail all of our plans at the end of the talk. Yeah, so again, just to caution, this is early stage in progress research. We are not, for instance, ready to propose any kind of drafts today. So for background, content distribution networks use overlay routing for a variety of benefits. So this is a diagram from Cloudflare detailing Argo, which is a product they offer. Argo is their name for overlay routing. And so what this does is, rather than having a user connect directly to the origin destination over the default route that the internet gives them and their ISPs and the autonomous systems along the way give them, the user connects to a Cloudflare server, and that Cloudflare server connects to another Cloudflare server and proxies the traffic that way. And this effectively lets Cloudflare choose the path through the internet rather than just using the default path handed to the user. And the benefits of this are there's a couple of them. One is perhaps better latencies. One is you can avoid temporary congestion. You can avoid permanently slower paths. You can avoid outages. In some circumstances, you wind up being able to multiplex traffic for a better overall throughput. And so Cloudflare does this. Akamai also does this. They call their product SureRoute. And so what lets them do this, and why do they get a benefit from it? Well, Cloudflare, Akamai, CDNs need to route a lot of long paths. And so these are long in two senses, geographically and in a network sense. And further, you need to be able to use your machines as proxies. And these machines need to be widely distributed across the network. And again, Akamai, Cloudflare et al. Have an enormous distribution of many, many, many thousands of machines all over the internet. They're all very powerful, and they have and so they have many potential proxies to use, but they also have a global view of the internet. They can sort of in real time they can assess network conditions and use those to choose better routes. And so our observation is that Tor meets several of those conditions. So Tor is an anonymity network. It's got 2 million daily users. And importantly for our purposes, it has about 6,000 what they call relays, which are nodes in the Tor network. And further, traffic in the Tor network needs to travel between most pairs of those relays. That is, pick any two, no matter how far away in the world, they probably are, or many of them are going to need to talk to each other at some point, and they're not choosing which ones talk to each other based on who's near each other in the network. And so our proposal is to introduce this overlay routing technique into Tor. So this diagram is a high-level overview of what's happening in Tor. A user is going to connect to a Tor relay or node, which is going to connect to another Tor relay or node, and another. And then finally, it'll spit out that traffic and send it to the destination. And all of this traffic in between is encrypted. We're proposing to not alter the way that Tor path selection works, but rather use the same path but introduce an additional hop only for the purposes of routing. So traffic between the first and the second relay will remain encrypted, but it'll be forwarded and not decrypted through a third, what we call via node. And again, this will give possibly many of the same performance benefits as in CDN. So latency, perhaps throughput, perhaps better use of bandwidth, perhaps more reliability. And our early analysis suggests that there will be minimal security impact. Yeah, and so again, importantly, we're not proposing, there are many other orthogonal proposals to alter Tor path selection for reasons of either security or performance. And we are not proposing any changes to that. We're also not adding additional encryption hops. We're just adding additional hops for routing. So when is this going to provide latency improvements? Well, it's going to do that when the direct path is slower than the path from A to X, then from X to B. So namely, like this wouldn't happen geometrically. It's never going to be faster, or geographically. It's never going to be faster for me to like walk to my destination via some other point than it would be to walk directly. But on the internet, in fact, this actually happens all the time. And we have some preliminary evidence that within the Tor network, it does happen. So we have some data. This is from a project called Ting from 2015. Their data is public, and we have some analysis of it. So they collected latency data between all pairs of a small subset, 50 nodes in the Tor network. And of those, we find sort of these latency speedup conditions in many of them. And kind of as you'd expect, in most cases, these speedups are very, very small. But you do find some paths. There will be a pair of Tor relays where the default traffic path is over 100 milliseconds slower than you could get by routing via some other node. And so we just, from that data set, we mapped out a couple examples of large speedups. So the default route from this node looks like the US East Coast into Scandinavia takes 200 milliseconds, but it turns out if you go via mainland Europe, you can basically have that. And so what this suggests is that the default route being used is slow and could be improved. And you see that again over on the right side of the screen. Yeah, and so we also observed that many of these pairs of nodes, their default routes are really bad. So in this example, 34 out of the 50 relays, when used as intermediate nodes, would provide a speed up. So the default route is worse than choosing another node in the Tor network at random to route traffic through. And again, this just indicates that whatever default route is coming out of this relay to the other relay is particularly bad. Yeah, so this data is all from 2015. It's a little out of date, and it's pretty small scale. So we really want to scale up measurements of pairwise latencies in the Tor network. So we've been in communication with the Tor Research Safety Board. We have their permission to do this experiment. And the next step also is we want to make sure it's actually secure. So most existing Tor security metrics that are used in academia to try to quantify the impact of various changes to the Tor network aren't affected. We think that like they are not affected in any way. We think that's not quite right. We think that there must be some impact to doing this. So we're trying to adapt some existing security frameworks and make sure we can quantify exactly how bad the risk of de-anonymization gets when you do this. And then we also want to make sure not only that it would work in theory, which you can learn from these pairwise measurements, but that it would work in practice, that it wouldn't impose unrealistic additional bandwidth requirements or computational requirements at these nodes, which are not commodity server machines often. They're often sort of running in a home network. And so in order to do that, we need to both build out a proof of concept and assess the performance impact, and then run simulations using the topography of the Tor network. And then in the future, perhaps this will be very promising and we would actually want to build this out in the Tor network. In any case, I think this is of independent interest for a couple of reasons. These Tor network latency measurements feel like a useful data set for worrying about Tor de-anonymization. And finally, we hope that this generates some interest in using overlay routing techniques in other decentralized systems. Yeah, so that's what I have. Happy to answer any questions.
Looks like Wes is in the queue. Wes?
Yeah, thanks. That's a really interesting concept and idea. I need to, wrap my head around it a little bit more to figure out how you would actually execute it. The CDNs have a lot of ability to sort of control those overlay networks. And so in your diagram, you kind of indicate that there's these hops where middle Tor nodes are actually making a decision about what direction to send something. And so one of my questions is it actually, can you trust them to actually make the right decision, right? Because they actually may take the slower path because they want to inhibit you, whereas that packets don't go through, but you don't really have a good way to measure whether this is actually helping, right?
Yeah, I suppose I'd argue that that's already the case, that if any of these relays, I guess you're just increasing the number of relays that could do this, but any of the relays in your Tor path have this capability to artificially slow down traffic already. So I'm not certain what the impact is beyond increasing the number of relays that might do this is. Maybe I'm misunderstanding.
I think that you're getting the point. I'm not sure. So I haven't looked into how much can an existing relay, slow down traffic in the first place. I mean, that they can certainly hold on to things longer in the first place, but okay, thanks.
Yeah, I believe that's roughly equivalent from at least a theoretical point of view. Whether it's equivalent practically, maybe not the case. All right. Any other questions? I'm not looking at the chat. Sorry if there's anything there. Oh, let me take a look. Oh, sorry.
Yeah, there's sorry, I've got a different room. There's a bunch of conversation in the chat where Kyle's been answering a bunch of questions about. So, for instance, can you deploy this just by modifying the client to change path selection? And then David asked a question about how do you compute the route so that not everybody goes over the faster route and then makes it slow again by overloading that port in the middle.
Yep. Yeah, so that's a great question, both of those. I'll start with the latter, which was how do you make sure that you don't do this in an overwhelming way? And so that's what our simulations are going to hope to answer. Our vision is that this will be a very edge case. We're hoping to help with tail latencies in the kind of 95th percentile or so, and we're not expecting that most hops are going to be affected by this. And if that is the case, then hopefully the overall impact, both on bandwidth and kind of on those individual nodes, would be relatively low. Also, these, I guess that's a segue into the next question. So these decisions would be made roughly in real time. So these nodes might have a list of candidate intermediate nodes in the path, but they would actually make those decisions based on sort of data races. This is how it happens in the CDN context. And so they're informing the final routing decision based on real world network conditions. And then, sorry, the first question was, could you do this client side? Yes, you could absolutely do this client side, but there are a couple of problems. One is the clients don't have this view of the network. And it would be possible to distribute these sort of pairwise latencies to the clients and let the clients use that to inform their routing decisions. That's additional hassle, and it doesn't capture anything in real time. And the other issue with doing it client side is you would do that, but you would do that by introducing well, you could do that with essentially no modification to the Tor servers by making only client-side software modifications. But that would involve extra encryption hop at these vias, which would increase the latency probably overall. It would probably wash out most of the benefit from doing this, that extra encryption step.
Any other questions for Kyle and Zach? We are at time, so that's perfect. Thanks a lot, Zach and Kyle, and also for like the great tag teaming with the answering questions in the chat. I think there's a lot of discussion that happened in the chat, and there seems to be a lot of interest. So yeah, we hope to see further iterations on this work.
Yeah, we'll hopefully keep you updated as it progresses.
Right. Thanks a lot. Is Stan here? Stan?
Hello.
Hey, I believe you don't have slides, but yeah, okay, awesome.
No slides. Hi, everyone. I'm Stan. I am a policy attorney from the Center for Democracy and Technology. I am not a technologist, so I'm a little out of my depth here. I want to present sort of the latest status and updates on the survey of censorship drafts. I'll start with a brief history and a description of the drafts, then talk about sort of where it is now, and then sort of our plans for bringing this draft to a close. This draft was authored primarily by my former colleague, Joe Hall. It is a survey of techniques used in various places around the world by network operators to block certain communications at the behest of or under the duress of sort of state actors, hence the use of the term censorship. Part of the issue, the larger issue with this draft is that in order to keep it as an up-to-date resource, because of the constantly evolving and emerging nature of censorship techniques, it requires someone to either be on hand to sort of provide regular updates to this, or for it to otherwise be a living document in some fashion. We have found that to be basically unsustainable for at least the original authors. And so I believe we have reached consensus based on the list to sort of bring this to a close, date it as, last updated as of a certain date, and then let it be what it is after that. Where it is now is almost there. I believe there are about 12 issues open. A lot of them are sort of minor debates about terminology, updating some references. There are a few larger issues to resolve about terminology and relationship between things. But I don't think any of them are too major of an issue. So, as I said, I'm a lawyer. I am able to resolve some of these. My role in this so far has been mostly as an editor, not a substantive contributor. So I can probably fix a lot of these that deal with sort of updating citations, substituting in a few extra words, or swapping out some terms. I'm less able to deal with resolving technical issues, but I believe we have some volunteers here in this group to sort of help me out figuring those things out and then bringing these to a close. So that is, those are my plans for trying to close this document up. I guess I would ask, please don't add any more issues, although we would like it to be, as current as possible, but the idea is to sort of tie this thing off and then let it be as it is. So that's it. I hope that I can get some time spent on this in the next 3 or 4 weeks, but I'm especially crunched at work these days, and so this is this continually falls lower on my priority list than I would like. Happy to answer any questions about that or say more if that would be useful.
Thanks a lot, Stan, for both your and other authors' work. I think we are at time. We don't have any time for questions or comments, but unless that was very quick, Joey, like we're literally at time.
To mark the remaining issues by priority, like the ones that you won't be able to get to until later on, and then maybe we can try to tackle those on first. That's all I wanted to say. Thanks.
That sounds great. Thanks, Billy.
Thanks, Joey. And yeah, we can continue iterating on this. And yeah, it'd be great if you can just kind of push this out after so much work that folks have put in. And the idea is to publish a snapshot, yes, for them to be like, this is up to date as of this date. And yeah, we can do a last call for that soon, right after the authors have had a chance to look at the existing issues. And with that, thanks all for coming to Pearg at IETF 110, and hope you have a great last day of IETF. Thanks all. Bye.
Yep. Thanks all.